So, welcome to the first week's or the first lectures lab about basically transfer learning and image classification and transfer learning. We will start the lab by speaking first about what transfer learning is, what, for example, things like ImageNet competition was, and how did it spiral into this big challenge to perform or to improve the CNN models in image classification. We'll start speaking a little bit about some of the winners of these of this challenge and how can we get started into using them very quickly in PyTorch without really needing to tune them, or as we were speaking it last time, we were speaking things like stride and padding and using max pooling or not using max pooling. All of these questions are already taken care of by these Facebook engineers. But still, it would be nice, of course, since you guys are not really just here as a tutorial, but you guys are students with a degree. So it's important for you to understand the components of these models from the inside. So let's get started. Does everybody have access to this lab? On Telegram, you could use some of the reactions if you don't want to talk. Nice.
Excuse me, can you repeat, please? What did you ask? Because sound missed.
Yeah, as I understand, we got some internet connection
Really?
errors. Yeah.
Oh, okay, got you. Let me change my location real quick. Maybe I'll have better internet. All right, is this better in terms of like hearing me? Okay, that's nice. That's great. So I was just saying, does everybody have access to the lab, like on Telegram?
Yes.
Yes.
Okay, that's nice. So for the lab, usually, and for the majority of the homeworks that I will be giving out, and even for your projects, if it's possible, please always try to use Colab for now. Probably during this, like the middle of the semester, somebody from the university might propose to us a, what is it called? An equivalent of Colab that is hosted by Innopolis. But for now, all the info that we will be doing when it comes to practical exercises will be done on Colab. Does everybody have like at least used Colab before, or nobody has a clue? Yeah, so yeah, Colab is pretty famous, right? So let's get started then with the lab. Yeah, the lab's structure is pretty simple. First, we will speak about things like image classification using transfer learning, what ImageNet is, the winners, and how to use some of the pre-trained models in PyTorch, and how to do the task of fine-tuning, which is highly related to transfer learning, right? And then we will see the PyTorch example, exactly the code, how to do it, followed with a old TensorFlow example, just so that people who want to know what are the differences between PyTorch and TensorFlow, at least they will have some idea. For now, there is not really a significant difference in terms of the frameworks, structure and components and the way of thinking about things like the data and the models and the computational graphs and everything. But the differences in terms of speed are also extremely small, right? There is no one better than the other. So it's up to you. If you prefer to use PyTorch, use PyTorch. If you prefer to use TensorFlow, use TensorFlow. And if there are some like requirements from the company that you're working with or something like that, then just work with what you got, right? So from my side, both of them are just equivalent. You can use anything you want and you can pass the scores with complete ease. So let's get started. So yeah, ImageNet was one of the main reasons why we had this big development in computer vision starting around 2012 till, let's say, 2015 or 2016. Those were the days where computer vision was the biggest or the highest field of artificial intelligence. Now, sadly, that honor has left to natural language processing, but hopefully computer vision will make a comeback soon. But the main reason why we did have that big, gigantic, as we said, improvement in computer vision goes for this new data set that is called ImageNet, which is a gigantic data set of up to, over 500 images for each class. And there were around like 1,000 classes, right? So as you can imagine, this is a gigantic data set with like millions of images, which is something that we did not have before, or we could not afford to train on before 2012. But thankfully, somebody built this data set. It was a very big work to build it. And the data set contains things of the following classes. So basically, the data set is built from a very also famous data set that is called WordNet, which provides a hierarchy of words. Only nouns were selected, of course, for the ImageNet data set for computer vision. And you see, for example, like mammal, you have lots of images for it, and then you go inside the mammal hierarchy, and you see placental. Inside of it, there are carnivores. Inside of it, there are canines, and then there are dogs, working dog, and of course, a husky inside that hierarchy. So you go, for example, for vehicle, and you've got a craft, and then a watercraft, and then a sailing vessel, a sailing boat, and I don't even know what this thing is, right? So it's, as you can imagine, it's extremely detailed and provides a very great opportunity for computer vision models to learn something extremely useful. Now, going to the winners of this challenge, majority of them are either Google, Microsoft, or someone as big as these two. And the first winners started with AlexNet around 2012. And that was the first time that we got, as you can see here, from 2011 to 2012, we got just a crazy amount of improvement in terms of error. So we went from 26% error to 16% error. And that was basically the time where everybody realized deep learning is the way, right? So deep learning is much better than, let's say, support vector machines, or much better than things like, what are they called? Decision trees, or more traditional approach, or a shallow approach, as it is being referred to in here. So here was the big boom for deep learning, and that's where the comeback for deep learning models. After this one, AlexNet, which is the traditional architecture that we have been seeing since last time, right? So this was the architecture that we have actually presented. We were followed by ZFNet, which is just very similar too. And then we got new architectures with very slight or small changes into their architecture, mainly, having things like bigger or much more, layers or deeper neural networks. So going with the VGG from, I think it was Google too. And then following that with the GoogleNet, which is 22 layers, and it was just a slightly better model. VGG 19, as you can see, is not the winner for 2014 competition, but it is still being used much more than actual GoogleNet because it's a bit smaller, and it provides very good performance, things like transfer, style transfer, and even transfer learning till now. And then you go to the crazy realm with ResNet, where they started going into numbers of layers that we did not see before, right? And this was with 152 layers. And this was the first time that computer vision model outperformed humans in the error. So now we have, as of 2015, we had models that are working much better than actual humans. And till 2017, the error was going down, and it continued to go down even more And now this challenge is no longer actually useful, mainly because the error is super low. And the only problem with this data set, or the only reason why we have an error in this data set, is because of error in original labeling. So they just, the data set itself had issues, right? If not for that, we would have like 100% performances on such a data set. And here you could just check live performances, let's see. So you see the top one accuracy is a bit bad, 91%. But if we go to the top 5 accuracy, here you'll see that we're like 99.02, 98, 98. Yeah, so we're we're doing pretty well, right? So it's less than 0.9 something percent error, which is amazing. And the only reason why we use the top 5 accuracy and not the top 1 accuracy, because in the same image, you could find a dog and you could find, for example, a cat and something else. So as long as the model is able to find, the class that we are looking for inside that image, then we consider that an accurate assessment, right? So as we were saying, the only reason why this data set does not have like 100% top 1 accuracy is only because we do not have a good data set for it. So it's not as simple as we would expect it. And here you see 99.02, and here it's 90.02. I think the best accuracy for this one is 91.01, and you can see the number of parameters sometimes just becomes crazy, right? So the higher number of parameters is, okay. So it goes up to, or goes down till 1.2 million, which is the smallest model. And here we can see it's like, doesn't have that good of performances. But the good thing about this one is it's mobile compatible. So it's very easy to run on your mobile. But if you want something really good and performant, as you can see, the number of parameters goes to like exponentially higher. And that is because we are training something that is really, really big. So for example, this one, you have almost 1 billion parameters. So just fitting this model into a mobile is completely impossible, let alone running the model on actual data, right? Let's go back to that. So yeah, this is the story of basically ImageNet and how it completely revolutionized the field of computer vision and provided us with the opportunity to basically have amazing neural networks that actually work very well and outperform humans in some tasks. Now, the question is, or something that we have seen already in this experiment and also in that link, all of these models are extremely gigantic. And as we said, even this small data set, the ImageNet data set, which is relatively small compared to the new data sets that we have right now, this one cannot fit into any laptop that we own, like me and you guys, right? And it does not fit into something that even our university, if you go to Innopolis University and ask them for like a good server, would be really difficult for you to get access to a server that actually hosts this data set, let alone train such models for weeks, right? And this is why, thankfully, somebody came up with the idea of why not use the models that are already trained by Google and Facebook and Microsoft, but only train them a little bit so that we can leverage that incredible amount of knowledge that they have gained. But for us, we will train them just a little bit more, for example, on our specific data set, right? So here they are being trained for how much? For 1,000 classes. But you are, for example, training them to detect COVID in MRI scans, let's say. So you have only 2 classes, yes COVID, no COVID. In that case, your data set is much simpler than, for example, ImageNet, right? So the accuracy, the base accuracy that you could get for a random model, let's say, would be 50%, imagining that we have clients balance. But for the 1000 classes, then your random accuracy with a class balance would be around 1 divided by, so it would be like 0.1%, right? So as you can see, going from a random accuracy of 0.1% to a situation where the random accuracy is, let's say, 0.5% is a very big improvement or simplification of the learning task. This is why using or leveraging this model that was trained on thousands of classes for weeks on and months sometimes provides a great opportunity for such smaller tasks. First of all, you will be able to leverage, as we said, that intelligence that was gathered there, and it would save you a lot of training from scratch. It would save you a lot of time to do configurations of stride, padding, etc. And to do that, thankfully, we have PyTorch that already implemented all of their architectures in the same package, and it allows us quick access to all of those architectures. So let's say, for example, I want to download anything from this Torch Vision models. Torch Vision models, for now, we're only going to be using them for image classification, but just keep in mind, they have everything that you might think of for computer vision, things like pixel-wise semantic segmentation, object detection, instance segmentation, person key pointation, and video classification. So they already have pre-trained models for all of these. And as you can imagine, or as you can see already, we downloaded all of these models really quickly. And let me just restart the runtime again and download them again, just so that we can see. Yes, just so you can see how much weight each one of them is. Okay, so it's starting. Okay, for some reason it disconnected. So Colab is good and bad sometimes, right? Let's stop it. Interrupt execution. Okay, let's run this. Done. So we could not see the download happening because it already downloaded earlier when I started running it. But as you can imagine, ResNet 18, AlexNet, these are quite average in size. And then you've got things like MobileNet, which is way smaller than the rest of them. And you could go to models which are go up to 1 gig, what are they called? 1 gigabyte of size. Right? So the size can go from 13 megabytes to anything you want. And the very good thing about this one is it is written completely in a Pythonic way, so you can access it as if it was an actual Python class, right? So here, if you go for ResNet, you can actually see the whole architecture here, right? But let's say you have a specific research question that wants you to change this layer 1 into something else. So what you could do is ResNet 18.layer1, and you're not going to change all of layer 1. Let's say you're going to change only the first part of the layer 1. And you're going to change, let's say, the convolutional 2. There you go. So you got access to the lowest level thing that you could think of. And even this one, you could access things like its weights. I'm not sure how to do that. Maybe like this, or maybe you add something like here. Yeah, not sure how you actually access the actual weights. You can easily do that. I'm not sure if we will do it here, but we will be doing it for the interpretability class. We will do exactly what we just did here, where we access the actual weights of each layer, and we will access even the gradients that are being calculated using backpropagation for each layer. So you have access to all the information that you want in a very Pythonic way. And if you want to, for example, as we said, change only this convolutional 2D layer into something else, then you could just do like this. Sorry. Right. So you could do something like this, and whatever class you want to give, and whatever type of parameters you want to do, right? So it's extremely flexible, extremely Pythonic. This is something, for example, in TensorFlow when it first came out. I don't know when it did, but when we first started working with TensorFlow, this just accessing the layers and accessing different weights was something that is impossible to do. But thankfully, now we have PyTorch, and also even TensorFlow has now become flexible or more flexible to work with this. So the architecture, let's go to some of the layers, and maybe somebody could tell me what they already recognize in here, right? So can you recognize some of these layers, and what are the layers you cannot recognize?
Yep.
Yep.
What is basic block?
Oh, but just a basic block, right? Just a way to group different layers together, right? So instead of thinking of a single layer, now you are thinking in terms of a block, right? It's just a convolutional layer, another ReLU, and a convolutional layer, just all of them together as one singular block. So it's not a type of layer or a type of calculation. It's just something, you could call it like a function wrapper or whatever you want, right? It's just some way to organize your thinking, because as you can see, this sequence of one convolution followed by batch normalization, by ReLU, by convolution, by batch normalization gets repeated a lot during this architecture. So they, instead of like rewriting this code hundreds of times, they put it inside the basic block. That's it. Anything else you guys do not recognize in this architecture? Maybe stride, padding, kernel size, all of this, you're familiar with it, but something here, maybe you're not. What is it?
What is momentum and batch normalization?
So momentum, we're not gonna be discussing it right now. And for example, also the epsilon here, but these are just different techniques that you will be using to, or different parameters that you will be tuning to get better results. But just keep in mind, batch normalization is a technique that is used. You already did normalization with Professor Khan, for example, right? You've seen, so for example, normalizing the input between 0 and 1, or normalizing the input between -1 and 1, or normal distribution. Have you seen that?
Yeah. I know what batch norm is. I don't know what like the parameters of it, like momentum of time and stuff. Yeah.
And that's amazing. So let's go to its actual definition and see how it goes, right? Batch norm 2D, sorry. And here's the class. And here is the function how to calculate batch norm 2D, right? So here, let's see what momentum is. The momentum argument is different from one used in optimizer class. So this is not the same one. So for example, like Atom optimizer or something like that. And the conventional notion of momentum. Mathematically, the update rule for running statistics here is x new equals 1 minus momentum times x plus momentum times xt, where x hat is the estimated statistics and xt is the new observed value. So here I'm guessing this is just a technique that allows for like stability of normalization across multiple batches, but I'm not really sure if that's correct, right? So that's definitely something that you could look a bit deeper for the running mean and running. Okay, yeah, so just basically something that allows to, let's say we have first batch goes in, we normalize it, second batch goes in, we normalize it. Instead of normalizing each batch with the individual batch mean and the individual batch variation or variance, we keep a certain part of the previous mean and the previous variance, and it should allow the new calculation for the mean and the variance. And as more comes into the data and more gets trained, this running mean gets more, gets more importance overall, right? It's a good technique that allows more stability in the training instead of each batch having their own variance and having their own mean, right? Great idea. So since your friend already knows what batch normalization is, I'm assuming the majority of the team already knows what batch normalization is. Anybody not familiar with the concept? Okay, so I'm guessing everybody is familiar. That's nice. So let's see if there is anything else here. Maybe ReLU. Everybody familiar with what ReLU is? We did not mention it last time. All good? Okay,
Yes, of
let's
course.
go to the. Yes, absolutely. Go ahead.
I said yes, of course. We know really.
Okay, could you say it?
What
I could not
exactly?
hear you well. Exactly
We
what you just
are
said.
familiar with ReLU, its activation function.
Okay, so you're familiar with the
Okay.
concept of activation functions in general and with ReLU specifically. So everything else is good. So things like, I don't know, TONH and stuff like that. You already remember, familiar with these concepts, right? Yes, I'm guessing that's a yes. Okay, so good. So our image classification task is usually, or our image classifier, we conceptually think of it as two different parts. The first part is the encoder, where it contains mainly things like convolutional layers and the max pooling. And the second part is the actual classifier, which is mainly only fully connected neural networks, right? So only multi-layer perceptrons from like the last time we've seen it, right? Are you familiar with this naming of encoder, classifier, decoder, stuff like that, or it's a new terminology? It's not a new model, right? It's just that a new terminology. Are you guys familiar with the new terminology?
Yes.
Oh, that's amazing. Then that's great. That's amazing. Right. So here, as we said, we will have an encoder, which is basically just a couple of convolutional layers and max pooling, and the classifier, which is the actual part which will do the classification, and it is just a fully connected neural network. The output size, or the number of classes for binary multi-class or multi-labeling, is basically the number of output neurons, right? So how we define, so for example, if you have 1,000 classes, your output or the last layer's number of neurons is equal to that number of classes. If it was a binary setting, then you have just one and 0 or 1. If you have multi-class, let's say you have 3 classes, so in that case you will have 3 different neurons. And if you have multi-labeling, also it's the same situation as multi-class when it comes to the number of output neurons, but just the function that you will be using by the end for the loss function will be different between multi-class and multi-labeling. So here, for example, we will have 50 layers of convolutional, 50 convolutional layers. And let's imagine the situation where we have 5 fully collected layers. 4 of them will always be the same. The last layer, for example, it had 1,000 neurons because of ImageNet. Now it will have 50 neurons instead of 1,000, right? So now we do not have that big of a data set. We have a much smaller data set. So we will only change the final layer in terms of the architecture. And then the tuning, it's up to us, right? So we will start speaking about the fine tuning process a bit later on, but just like a heads up, right? We've already discussed this a little bit earlier. Since we are going to change the number of the classes because we're going from ImageNet to another data set, the last layer is obligatory going to disappear, right? Even if one of the classes is shared between, say, something like ImageNet and the new data set, then in this situation, it's much easier to basically replace that last layer with a new layer. But if you want, you can actually just copy the weights for that specific neuron for that specific class, since it's going to be the same, and keep that one as not tuned and the rest is tuned. But that will make your model a bit harder to train, because you will have to like keep track of two separate loss functions. But it's up to you. For example, if you have the class person, which is usually something that you will be doing a lot in, let's say, something like object detection, it might be worth putting in that extra effort to keep that class from the same original data set and not retune it on your own small data set, just for that keeping or maintaining that high performance in there, right? So yeah, so fine tune it on a data set, whatever it is. So for example, you have COVID, pneumonia, or lung. So your K is now the number of classes. Just replace the last classification layer with a new layer that has only 3 neurons or 3 output neurons. Fine tuning, as we said, is the task, or transfer learning is the task of training a model on a big data set and adjusting the parameters of that model for a small data set with a much smaller amount of data, right? So for us, as we said, thankfully, we have already hundreds of pre-trained models. If you go to something like RoboFlow for object detection, you will find at least, I don't know, at least like 50 different models that are trained. And even within those 50 models, you will find at least 5 to 10 different variations of that same model, right? So you have extreme amount of flexibility in terms of the pre-trained capabilities. Some of them are trained with ImageNet, others are trained on other big data sets. So it's also up to you to choose which pre-trained data it was trained on. But thankfully, so you don't have to retrain basically everything from scratch. And you could just train it for whatever smaller data set that you have, let's say a medical field data set or a music data set or whatever it is, right? The assumption or in computer vision, yeah, it is very common in computer vision, and now even in natural language processing with the emergence of BERT and UML Fit, and now even if you are doing something like ChatGPT or training something like ChatGPT, you might have already heard that there are different versions of ChatGPT, something that is trained only for the medical field, something else, another version of ChatGPT that is trained only for, let's say, lawyer-specific tasks or for, you know, some self-help or different versions of ChatGPT. They're all trained on the same concept of not exactly freezing the final layer. That's only for image classification. But in this idea of fine tuning, where we train a gigantic model on a gigantic data set, and then we just adjust some of its parameters to some more fine-tuned data sets with less data. So let's get to the code, right? So this is how you're going to do the PyTorch example. In PyTorch, there are 3 main steps. First step is the data reading. Second step is the model creation. And the final step, which I don't have here, but the final step is the training step in here. So let's just make it also a step. Think like this, 3 and training. Nice. Yep. So the first step, as we said, is the data reading step. In this step, you will have three main tasks. The first one is the building of the data source location. If you are using, as we will be doing here, if you are using a data set that already exists within PyTorch, this first step is almost zero work, right? So you're not going to do any work. But if you do not, and if you will be using your own data set and you have some specific logic for, say, things, how to choose the images or how to choose the order of the images and etc., then you will have to do the following, right? You will have to recreate a class similar to this one. Let's go to the actual code and see how it looks. It's actually pretty simple. Just remember to always implement two important functions. I think you could go to the code. Yeah, here, source. Here you can see the code. Always remember to, inherit from vision dataset class. And yeah, the length function, this is extremely important. You always have to implement it. And it should be somewhere here, the item or get item. Yeah, the get item function is always also something that you will have to get. The code is exactly how you will get it, whether you will download it, how you will load the data set, where you will get the data set, all of that, it's up to you. You could maintain some sort of a CSV in here. You could maintain a table, whatever you want to do, you can do it as long as you implement these two functions, get item and the length, right? So yeah, as we said, this task, pretty easy if you're going to use a toy data set as in here, but if you're doing this for an actual new data set that is a bit more challenging, then you will have to build that logic from scratch yourself, but it's pretty easy and straightforward. Just maintain these two functions and make sure that the length is calculated correctly, because it's always pretty tricky to do that. The second is to build the transformations and the data augmentations, right? So I'm not sure if you guys have done already what transformations and data augmentations are, and you've done that with Professor Khan. But for our sake, let's just take a look at some of the most common types of transformations using this library that is called augmentations. So this is my favorite one, especially for things like we're training, object detection models and stuff like that, because it provides some very beautiful just a very beautiful, as I said, API that allows you to work pretty easily. So let's say we have this image and we want to apply some blurring. Probably you haven't really studied blurring very well, but if you go for here. Okay. So as you can see right now here, it makes the image much harder to work with, and it allows the model to learn even deeper. So it's as if you are augmenting the size of your data set. Say that you have only like 2,000 images, which is not enough actually for training an actual model. But for fine-tuning a model, you are a bit more lucky. It could be enough, but it would be much better if you do some augmentation, and then you would improve your results. Basically, you would take the same image and generate like hundreds of versions of that same image. And that's a way of like tricking the neural network to thinking that it has more images than it actually does. So here there is the advanced blur. There is some blurring, also another one. Very simple. Channel shuffle, as you can see. So it just basically plays with the RGB channels. Coarse dropout, it provides some missing, locations in the image, and it's up to you, of course, how many. Color jitter, this one is pretty good. We usually use it a lot. See? So it basically provides all of the previous things that we've seen together, but in the same one. So this one with just one augmentation, you could just play all with these hyperparameters. And each time it loads an image, it will randomly apply one of these things in a sequence. And that would give you like a completely different image from what you started. Color jitter, defocus, downscale, elastic transform. See? So this one makes it even more challenging a little bit to the model to actually learn. This one makes it grayscale. Apply as many of these transformations as you can, because the more you apply, the better for your model. But just remember, for example, something like 6, if you rotate it too much, it might become a 9, right? So if you apply too many augmentations to your data set, thinking that you are helping the model, it might backfire and you might be hurting the model's performances. So that is the second step. Pretty easy step to do, right? So for majority of the cases, what you will have to do is to implement 2 very important transformations. The first one is transforms.toTensor. This one just converts whatever low data set you have. So for example, you have like a NumPy image, or you have some type of image from another PIL or just an image, whatever it is. Converting it into a tensor is obligatory for you to send it through the neural network or the PyTorch neural network. So you must be using the PyTorch tensors. The second one that is also obligatory or important to not forget is the normalization. And here we are using normalization based on 0.5, 0.5. This is the mean, and this is the variance of the channels. So this is for blue, red, green, RGB, red, green, blue. Sorry, yeah, red, green, and blue. This is the variance for red and green and blue. Of course, it depends on whatever model that you are going to use. So let's say, for example, you are going to train let's see which kind of model you want. Let's say GoogleNet. So what you have to do is go GoogleNet and say normalization and use the same normalization that they have used during the training. It could be a bit tricky to actually find it. Let's see. Here it is. Yep. So they normalized everything between this means and these standard deviation. So when you are fine-tuning this model, make sure that you are using the actual appropriate means and variations that they have used also for the training. This makes the performances much more stable for your data set. The last step is the data loader or the data loading process. For us, it's not going to be that hard to load the data. We don't care about the order of the data. We don't care about the sequences of the classes or all of these information. We do not care about that. So here, for example, for the test data set, we will do download equals true, train equals false. This is just so that we download the training data set and we send it the transformations. One thing to keep in mind is this function shuffle equals false. If you want to say shuffle equals true, this will be loading you different, different versions every time. So for example, here for the train loader, it never gives you the same order as before. But for us, since we are going to use this for the test loader, you could prefer to use something like shuffle is equal to false so that you always have very stable testing environment that does not change with the changes, right? Here you got something like, here's the train loader. And you basically just give it the batch size is equal to 32. Batch size is something that is pretty tricky to tune. Majority of the people use something like 32. Previously, the recommendation was use as big of a batch size as your RAM can afford. So especially the GPU RAM. But now there came some research that said if you increase the batch size too much, you're not going to get that much improvement on results. So it makes more sense sometimes to actually stay on the lower side, right? So things like 32, 64 is the maximum. 16 is like the absolute minimum, unless you have like a very, very big image and you cannot load that whole thing into the RAM. So you would use a batch size of like 8 or 4. But in the majority of the cases, just stick to something around 32, 40, 64, or 16. Number of workers is also related to how good your server is. So if you have a big server, use a high amount of number of workers. If you do not, then just keep like number of 2 or something like that. The data set, as we said, is pretty easy to load it because it's already exists in the actual what is it called? PyTorch. So all good. We downloaded the data set. Now let's show some example of the images. So here it comes. Yeah, here are some of the examples of our images. As you can see, we applied some what is it called? Channel jitter or color jitter, right? And it completely changed a little bit some of these images a little bit, right? So this one I think is a bird. This is clearly a cat. This is a car. This is a moose. A deer. Okay, this is a deer. And let's see, this is a truck, this is a car, a ship. So it still remains pretty recognizable, right? So now let's check if we got some, oh, we got a message. I think we should really apply transforms to the test data sets besides, absolutely. Are we applying transformations to the test data set? Yes, we are. Yep. So let's create that exactly right now. So transform. This one, let's call it transform train. And this one, let's call it transform test. Make sure that you keep the same normalization, but other than that, yeah, you should not apply any transformations to the test data set. And there we go. And this one, there we go. Thank you so much, Igor. And then Kareem said, unless we want to use test time augmentation. Yep, absolutely. So I don't think we will be using test time augmentation because during inference also we will not be doing any augmentation, at least for this, right? So it will make sense that we maintain, as your friend has suggested, as similar data as possible to what will be used during the inference so that we can actually get some objective estimation of the results of our model. So right now, let's just run NVIDIA SMI, and this one would just tell you whether you have a GPU or not. So we have a Tesla T4, which is very common with Colab, and it has 16 gigabytes of RAM for the GPU, which is a crazy amount of RAM, right? Which is really good. So it should be enough for us to train any object detection model, any segmentation model, any image classification model that we want, or even to fine tune some larger natural language processing models with big ease, right? So it's not really a major issue for us. Then we get to the next step, which is the model creation. The model creation, here you will have to define two things, which is the architecture of the model and the logic of the architecture. Pretty simply, you will have two functions. One is the init function, where you define the components. And the second one is the forward function, where you have to define basically the steps of going through your actual layer. So here we will have one convolutional layer. Here's the dimensions. This is just something that I set up. So here you will have something like, this is the number of kernels. I think this is the number of output channels. And this is the number of, or the size of the kernel. By default, it assumes a stride of 1 and a padding of 0. Yep, let's see, it loads. Yeah, input channels, output channels, kernel size, and then we've got stride is equal to, by default, to 1. Yes, padding by default is equal to 0, and the rest is not really that important. After that, we will have max pooling to basically reduce a little bit the calculations, and followed by a convolutional 2D. This is the second convolutional 2D that we see. And as you can see, the input channels for this one is the same as the output channels for that one. So max pooling does not change at all the number of channels. Here, the output, the number of output channels is 16, and the kernel size is also 5. Here, this is the first linear model. So here is our encoder. This is our classifier. In this case, they're both pretty simple. So let's just do like this: encoder, and this one is the classifier. Since they are very simple, we will keep them in the same class, but in most cases they will be very big, and you might want to split them very clearly and do some calculations between them, right? But for our case, it's pretty simple. So here we have 16 channels. Each channel is a 5x5 image or a 5x5 matrix. So our first linear, or our first fully connected layer will get an input of 16 by 5 by 5, and its output will be 120. The next one will have an input of 120 and an output of 84, and the last one will have an output of 84 and an input of 84 and an output of 10. Remember, 10 is our number of classes. Pretty simply, you will apply convolutional layer to the first to the input. You will apply a ReLU, and then you will apply pooling. exactly like this, and you put the output in the same variable as the input, right? So this allows you to maintain like an easier reading of this function, but you are not obligated to call this one x or x. Yeah, you could call it x1, for example, and put x1 here. Up to you. But it's just for the simplicity of the reading, you could name it the same as the actual input image. So one thing that is common to use is to, for example, for this final layer before the classifier, you could name it something like embedding, and the rest continues normally. But for now, we're not going to go that much into depth, and we will just be using X. Just note that after the second convolution and the second, of course, max pooling, we will be using something called flattening. And flattening just simply is you take a matrix and return a vector, one-dimensional vector. And this one-dimensional vector, its shape, as we said, is 16 by 5 by 5. And the -1 in here just refers to the batch size. So whatever batch size we have, we will be putting it in this -1. So it's like automatically thinks of it as fills it automatically, basically, right? So here we get the following. Put it through the fully connected layer 1, fully connected layer 2, ReLU, and then a fully connected layer 3 without a ReLU, and we return it. So let's see. Now let's check the architecture of our model. Net, like this. So here we have access to the architecture of our model. You could change it however you want. You can apply whatever you want. It's pretty easy to do, and it's very simple to maintain. Now, the final step is the actual training, right? So in the training, this one is going to be a little bit more tricky because we will have a very long function here. So first of all, do not get scared because all of this is just here to track the performances and stuff like that. This is not what you will actually be doing for the majority of your work. This here, for example, is just here to print or to plot a couple of images. Absolutely useless for the majority of the cases. What is extremely important for the training is the following, is to define a loss, an optimizer, a training loop, accessing the data and sending it to the GPU, and then passing the data through the model, calculating the loss. Let me just, calculating the loss, backpropagating the loss, taking one step of backpropagation, and cleaning up backpropagation, right? So these are the steps that you need to do. Remember, loss, optimizer, training loop, accessing the data, passing the data through the model, calculating the loss between the prediction and the real, backpropagating the loss, one step of backpropagation or a learning step, and then cleaning up the backpropagation. Here we will be using a simple loss, which is the criterion in here, which is basic cross entropy loss. Our optimizer is also going to be a very basic optimizer, which is stochastic gradient descent. It will be tuning the network, right? So here we call net, our network. So this optimizer is only optimizing the network's parameters. In cases later on, we will see adversarial training. And for example, this one will have an Adam optimizer. This one will have another optimizer. And different parts of the network are trained using different optimizers. It will be very important to understand why do we have this separation of this optimizer only trains this neural network or only trains this part of our neural network. Of course, the learning rate and the momentum here are used to make sure that the model is tuned pretty well. You could use a higher learning rate to train it a bit faster, but you might not converge. Or you could use a much smaller learning rate, but it will be much slower and it might never reach your destination. So this is why it's nice to have that perfect learning rate with a good momentum. So in this case, we're not going to train for a long period. We're going to train, for example, only for one iteration over the data set because we have a good amount of data and because we will just want to see the results really quickly. We go through the running loss. This is something that, for example, absolutely useless for the majority of you. This is just Python code. This is the actual training loop. This is the loop over the data set. This is the loop of the data set multiple times. So this one is the not batch size, what is it called? So for object detection, it's called max batches. And for image or for what is it called? For image classification, it's called epochs, right? So this one goes over the data set multiple times. In this case, we're going only once. If you want to go through the data set 10 times, you could put it like this. It's usually called epochs for image classification. And if you go to the object detection realm, it's called max batches. Pretty simply, you will enumerate through the data set. So this is the train loader. You will treat it as any other data source, as if it was an array, and you will basically get the data or load the data from it. The data is split into inputs and labels. And from the inputs and labels, you will send them through the device. In our case, the device is the GPU, which we have checked with NVIDIA SMI. Optimizer.0grad, we will keep this as unknown. What does it do for now? But remember, it is related to this, cleaning up the backpropagation. Once we see what the backpropagation does, we will understand why do we put this here. So pretty simply, we will take the inputs, put them through the network. So inputs inside the network, immediately we get the output. Very simple function, very simple logic, very easy to understand in a Pythonic way, which is really nice, better than what TensorFlow previously did. And calculate the loss between the outputs of the network. This is the predictions and the real labels. So we are calculating the differences between them inside this loss. Loss.backward actually calculates the backpropagated gradients. So the gradients of the optimizer. And then saying optimizer.step allows you to take the step in the direction of the gradient and update the weights of the neural networks in order to reduce the loss. Why are these two steps separated? Mainly because there are some techniques which require multiple gradients to be stacked on top of each other before you make one step of the optimizer, right? So you might want to do 3 batches and calculate the backpropagated gradients for 3 batches, and then make one optimizer step for all of them at the same time. So you can do that if you want, but if you do not want it, then always just combine loss.backward with optimizer.step. It makes for the ability to build more complicated research ideas in a very simple way that is extremely fast, right? So it runs extremely fast. Here we're just calculating the loss, which is extremely useless because this is just basic Python, right? The rest in here is also basic Python, which we will not need. Now we will go back to this idea of optimizer.0grad, and it basically zeros the parameters or the gradients of each individual layers. So all the layers inside this network.parameters have internal gradients, and basically calculated from the previous approach, because every time we do loss.backward, the optimizer.step does not clean the gradients, right? So it keeps the gradients there, it does not remove them. So it's your job to manually remove them. So you could either put this step after optimizer.step, or you could do it before the loss.backward. Personally, I prefer to do it before the loss.backward because in most cases, you'll be training a very big architecture and you risk having different parts of your code building different gradients to that specific part of the neural network, which should not happen, right? So just to make sure that it's easy to debug, easy to train, easy to understand, preferably put optimizer.0grad right before you calculate the loss.backward. And this way you make sure that nothing is affecting the optimizer.step besides this code right here. Easier to tune and easier to debug. Here, this is just some visualizations and building or calculations of, calculations of the accuracy, which is absolutely useless for us. Let's check. Okay, we built this function, and now let's actually train a singular model. For the sake of speed, let's continue looking into the rest of this and train it too. So first, let's check the difference between these two ideas, right? So here we'll first fix the same, the transforms only for test data. Let's go like this, or let's just maintain everything the same. All good. No. Here, yeah. Yes, all good. So it is still training. It might take some time for us to finish. But overall, so we will have the same transform train, we will have the same transform test, we will have the same data set, same data loader, same everything. The only thing that is now different is the actual neural network. And here, the actual neural network is pretty simple. So here, self.net is equal to models.resnet 18. So we're using a ResNet 18. It is a pre-trained ResNet 18, and this will just show you the progress once it's being downloaded, but it's already downloaded, so for us, it's not going to do anything. And what we're doing is we're setting this whole network dot trainable is equal to false, means that this whole network is no longer being trained. So what this dot trainable is equal to false will do is it will go as a hierarchy to each individual layer inside the self.net, and it will set the self.trainable equal to false for all of them. After we have done this, so all of the network is no longer trainable, meaning there will be no calculation of gradients, there will be no back propagation of loss, there will be no step of the of the gradients, nothing. Just nothing happens to the majority of the network. It is completely fixed. What we will do is we will replace the final layer of this self.network, the final layer, the classification layer, with an NM linear of 512 and 10. So if we check ResNet 18, let's go back to ResNet 18, ResNet 18, ResNet 18 should be here. The final classification layer, as you can see in here, the name is called FC, fully connected, just the final classification layer. Input features is 512. We will maintain this number of input features. I'm not going to change that, of course, but the output features is going to change. So for us, we're not going to have 1,000 classes or 1,000 output features. We will have only 10 output features. So let's come back. It is still training, which is weird. Usually it's pretty fast, but let's see. So yeah, so it now has only 10 output classes, and the forward function is pretty simple. So it's self.net.x. So it just sends x through the network. I do not know why it is being super slow. Let's start with this one. Usually this one is much faster. Okay, all good. I mean, the data set is pretty big, but I expected it to go much faster than this. Other than that, we have the TensorFlow example. It's pretty simple. It follows the same logic as you have seen already in PyTorch, but this was the previous way of doing things using Keras, very ugly. So basically, you would define both the logic and the, what is it called? So you will define both the actual layers and the order of the layers and the same code, which is pretty easy for small classifiers. But if you're building something that is complicated or some architecture that might reuse the same layer in multiple places, this structure was completely useless. So for research purposes, TensorFlow was extremely hard to work with, whereas PyTorch just blew up in the field of research, allowing for much better results. And here, this is the old way of doing things. They really hated it. Everybody hated this old way. And now in TensorFlow 2.0, you have the same exact separation of classes or of components and logic. We have this amazing flexibility that allows for like the dynamic graph to be created. And for example, here, if you want, I don't know, here, right? Let's say if random something bigger than 5, then you go through fully connected 1. If it's not, then you go through something else. Or you could do for I in range 20, send it through the same layer again and again. So basically in this code, you are allowed to use any Python logic that you might think of. And this is the powerful thing about PyTorch, or the powerful idea that PyTorch has brought in compared to, let's say, this architecture, which is pretty rigid, right? So here, there's no way to access the actual X of the, or the input at real time and do different operations based on that input, right? Where for us here, you only have code, logic, structure, everything is fixed. But thankfully, they learned from their mistake and they adopted the same techniques as PyTorch, and now the code works in an extremely similar manner. This one is pretty slow for some reason. But since we have some time, how much time do we still have?
20 minutes, I guess.
20 minutes. So let's switch to talking a little bit about your projects and discussing your projects, or maybe if you have some questions about the lab for now. What's going to happen is once this code runs, you will see that this pre-trained network, this one, provides much better results than the network that we have built manually than this one. And it's much easier to train. But sadly, since they will both take at least a couple of minutes to be trained, we will have to wait for their results. Any questions about the lab?
Can you hear me?
Yes.
How can we remove a layer from the net? Not to replace it, but to remove it.
Completely remove it.
Yeah.
That's a little bit tricky because the following, right? So what you have is this separation of logic from, what is it called? From actual code. So here, if I have just this layer that I want to replace or I want to remove, I can just say the name of this just object, right? It's just an object of the class, and change it. And without changing the self.forward function, right? The forward function remains the same. I can easily remove it from here or replace it from here, and the forward function remains the same. Hopefully, if I replace it correctly. But if I'm going to remove it completely, then I will have to rewrite the forward function manually, right? Does that make sense?
Yeah, but doesn't we have any like maybe some tricks which will allow us not to change the forward function, but to look at this layer like it's removed one?
Yes, that's the thing, right? So for example, if I remove layer 3 from here, just removing it, I can remove it, right? And say that I want layer 2 followed by immediately layer 4. That would lead to the output size of layer 2 not being expected by layer 4, and then you will just have a bug. So it's just completely impossible to actually run your code anymore. But I'm not really seeing the situation where you can just remove a certain layer without a change in, so for example, things like the output size or something like that, unless you are using some very good padding to make sure that the same output size is maintained for all of them.
I think I can probably answer a bit like more.
Go ahead, yeah.
I think, Daniel, did you ask about like pre-trained model?
Yeah.
So basically you can treat model module, in this case, as an iterable, and remove layers like elements in array in Python. And if if layer sizes are match up, there will be no problem in forward
Yes.
pass and backward pass.
Okay, I understand.
Did you get that? So
Yeah,
yeah, you're
that's
absolutely
sorry.
correct, but the only condition is that that the layers must have good padding or good enough calculations of padding and things like if you see something like max pooling, immediately the idea just no longer works, right? So it just completely impossible to remove a certain layer if there is something like max pooling in there, right? Because it drastically reduces the sizes of the output. So just make sure if you want to replace a layer or remove a layer completely, that the sizes remain the same, right? And also another very important thing is if you are removing a certain layer, that layer was doing some processing, that was doing some logic in the pre-training, right? In the pre-trained model. So if you remove that, layer 4, if you removed, for example, layer 3 and just did layer 2 followed by layer 4 is now going to receive a new type of distribution that is different from what it was trying to understand before. So everything after layer 2 will have to be retrained from scratch, right? So if you remove a certain layer from the middle, it's going to absolutely need to be retrained. Everything afterwards, after that one, will have to be retrained, right? So if I'm understanding correctly, what was the goal though of removing a layer instead of replacing it? Okay. So I guess if the goal was simply to reduce the size of the network, then as your friend Kareem has suggested, this relation works pretty well too. If the goal is to remove like the final 12 layers and only use the first 10 layers because you're doing something else. So for example, you take something like this, you take a ResNet 18 and convert it from encoder classifier to encoder decoder setting, then that's also completely reasonable. So you will be removing everything after, let's say, layer 5 or something like that, and building a new architecture afterwards. So not replacing individual layers, but completely removing them and stopping at a certain point, right? But for each one of these situations, you sadly have to rewrite the forward function, unless they are, as your friend has suggested, unless they are being calculated or the structure of the thing is done using a array like architecture. And in this case, you could just remove the third layer and it will just continue in the array pretty easily. So I hope that answered your question. Anybody else has a different question? Mm-hmm. I think it's this one that is taking the majority.
I have, may I ask a question?
Absolutely, go ahead, yep.
Okay, it's a more general question. Do we need use it like one of the argumentation from our project? Is it obligatory or not? As I understand, okay, for example, on the current lecture, we talked about some transfer learning. Do we obligatory must need to use for our product?
So it depends, right? If you are using, I don't know, natural language processing, you're definitely not going to be using something like this, right? But if you are using images, in most cases, it does help your model, something that you at least experiment with. But if you believe that it's not really important for you, then just provide a justification why you do not want to use it, then we can go for it. Yeah, that's easy.
Okay, got it.
Any reason why you don't want to use augmentation? Is it like specific to your type of data set, or is it because you just don't want to put those 2 lines of code, right? Because it's pretty simple, right? It's just a couple of lines of code. It does take some calculations on the, what is it called, on the CPU side. So you might need some good CPU to actually run this fast. But other than that, there's not really a big harm in actually using augmentation. All good?
Yeah, thank you.
Perfect. So yeah, sadly, this code is going to take some time to actually run fully, but let's hope we can see the results by the end. Let's go to the actual Google Docs and see how the progress is there for the project. Nice. Everything seems good here. Pick to recipe with pick to recipe with ChatGPT. This seems cool. How are you guys going to feed a picture into ChatGPT? This is mainly for Karina and Layla.
Sorry,
I
can
think-
you repeat the question?
How can you feed a picture into ChatGPT? I think the current version of ChatGPT does not allow for such.
No, first we will train the multi-class
Oh, wow.
model, and next we will prompt ChatGPT IP to provide a recipe and something.
Extremely smart. I love this. Yeah, that's amazing. Great idea. That's perfect. Or you could use something else other than ChatGPT, something that is actually multi-model that works both with pictures and with images. With images and with text very well too. Something's like those same versions of ChatGPT, but like different, coming from Google, for example. They provided so many good open source models that work with both pretty well. But yeah, that's also a very good idea to build a classifier followed by prompting for ChatGPT. Amazing. Let's see. Detecting arrival and presence and departure of vehicles in a factory based on a video. Amazing. What is TBA? So we've got Yezen, not yet doing. Optical chemical structure recognition, that's great. Face recognition pipeline, amazing. Real-time computer vision system customized for UAV for counting architectural goods. That's wonderful. Wow. AI for personalized learning, amazing. AI for visual novel, perfect. Recognition of marking elements of pipelines on the basis of a photo, amazing. Healthy based productivity, cool. CV computer vision search engine, amazing. This is really extremely useful. This search engine thing is pretty cool. Real-time detection of passing trains from multiple cameras, cool. Logiflex, I like the name. Get more by using AI. I don't know what you can get more, but I am down with it. I like it. Applying neural networks to compress data. Okay, so autoencoders could be a good idea. That's great too. Mushroom identifier. I hope it's legal. Mushrooms. Question answering. Generation and recognition of patterns made of lines on a sphere. Okay, so this is, I think this is traditional computer vision, right? It's mainly for Alexander. Maybe he's not. Oh, wait. Yeah, you guys are here. Yeah, let's see. CV. Ah, resume. Okay, CV is equal to resume. Yeah, yep, absolutely. Yep, I got you. Yes. Okay, computer. So CV, resume, search engine. Okay, nice. Very nice. American Sign Language recognition and generation. Okay, perfect. So I'm seeing that the majority of you have got some ideas some of you have already built your report, and it's pretty well built. I'm seeing the majority of the reports look nice. Neurofiction, pretty nice. And you got some pictures. I love that. Yeah, put pictures in the report, makes it easier for me to grade, at least less. Okay, nice. So I guess there is Yezen, who still did not put an idea for his project. And I don't understand what TBA is. So I guess only two or three
TBA
people.
means to be announced, I guess.
To be announced. Okay, so to be determined. Nice. Okay, so we got 3 people who still did not find all the answers, but yeah, you still have 2 days to basically finish all of this up and hopefully present to us your idea, hopefully on Monday. And this Monday, we will release the first homework, and basically the homework is going to be pretty simple. Also, we will start our first lecture on image interpretability and interpretability in general. So first, interpretability for tabular data sets, so for Excel-like data and CSVs. And then we will speak about interpretability for text data. And then finally, we will speak about interpretability for computer vision data, or majority is image classification data, right? After that, we will have the lab also on the next Sunday, and the same way we will release the second homework on the Monday afterwards, which is again just basically just doing the lab again twice, or the lab is basically image interpretability. So you will be doing exactly that. So you will try to interpret, you will build your own model and interpret why it doesn't work. That's the question. After that, we will probably switch to trading object detection models, and we will speak about natural language processing and the second half of the course. So sadly, the lab is still running, and it's definitely not going to end anytime soon. But hopefully, by the I will share with you guys the results of the next of the running after it finishes running, right? But pretty simply, what you will get is the following. Training an architecture from scratch will lead to very bad results, and fine-tuning this data set or fine-tuning this on the same task will give you much higher accuracy. So perfect. Does anybody have any questions so far about the course in general, about the lab, about the project specifically?
Sorry, am I right that you were talking about the
Sadly.
the lecture on Monday?
Absolutely. I was speaking about the lecture on Monday, thinking that we will study, but apparently it is a holiday, right? So it's it's the Russia Day, right?
Mm-hmm. Also, I have a question. What should we submit on Moodle for this report?
Yeah. Nothing. You will not be expected to submit anything on Moodle for this report. You could do something. Let me just check again. Maybe just a simple done or a simple link to the report or something like that. Let me just confirm, because I did do it and then I changed my mind. Let me see. My courses. I thought it's well explained, but let's check again. Summer 2023, and we've got where is it? Assignment, project ideas. So here, create the groups, choose the project, write the report from the following information, fill in the information here. I think just like type your report link or something like that, and that's it. Just send the link to the report, and that's it.
Okay, thank you.
Thank you. Perfect. So I see already 15 people have submitted their reports. That's great. Perfect. Any other questions? I guess that closes today's lecture. So enjoy your weekend and celebrate enough, and happy holidays on next Monday. Bye-bye.
Thank you.
Bye bye. Thank you.